Hello everybody. Today we're gonna have our second guest talk of this series. So today, let me introduce the speaker. His name is Sergey Ivanov, and he obtained his PhD in computer science at the Kolkovo Institute of Science and Technology. And actually, he is currently working as a senior researcher at Criteo, working on graphs and also applying geometric deep learning in industry scenario. So today, I guess the title should be something like Boost Then Convolve, Gradient Boosting Meets Graph Neural Networks. But I will leave the floor to Sergey, and so he will tell more about this boosting and graph neural network techniques. Sergey?
Yeah, thank you, Giovanni. So let me share the screen. Hold a sec. Okay. Yes. Hello, everybody. So today, as Giovanni said, I will talk about the work on combination of gradient boosting and graph neural networks. This is a clear work, and I'll try to go into more details how the whole pipeline and the whole architecture works. If you have any questions, please let me know. You can interrupt me during the talk or ask it later. So before going to the talk, I'll first give a few facts about me. So I lived in 5 different cities in my life. So 2 of them in Russia, where I grew up, and then also lived in Hong Kong for a little while, in Boston, and now I live in Paris for more than 3 years. I obtained degrees first in math, so I studied mechanics and mechanical engineering, and then in my master's I did more of computer science, and finally I did my PhD in machine learning and particularly graph machine learning. And also I have a lot of promotion of this area to the external people. So I have the blog posts, you can find them online, you can subscribe to my newsletter, and also Telegram channel where I try to post up-to-date information about this area, the papers that appear, the facts, and so on. So the outline of the talk will be first to give you a little bit of background on graph neural networks and gradient boosted decision trees. I would expect that most of you already know well graph neural nets, and I'll pay more attention to gradient boosted decision trees because I think for many it's only high-level ideas that are familiar, and the details of gradient boosted decision trees are not clear. Then I'll speak about our architecture, which we call BoostGNN, and then we'll show that it works in practice in the experiments. So a little bit of motivation of graphs and ML. So graph machine learning now is a very hot topic. There are many papers. I think it's about 300 papers on arXiv that appear that in this intersection of machine learning and graph theory. People use it for many areas of life, such as recognition of pedestrians or objects, for self-driving cars, for designing new molecules, for simulating physics, for social network analysis, and many other applications. In fact, I have written a post on this, so you can check it out on Medium. It goes into more details about different applications, and I think my hope, at least, that in 2021 we'll have, and in the future we'll have much more applications and showcases where GMNs and graphs in general shine. So now let's move on to the talk. We have 2 worlds of ML models, broadly speaking. So one is neural networks, which are trained through stochastic gradient descent normally. And the second type of ML models are decision trees. And they are trained in a very different way, which I will speak later. It's called gradient descent in functional space, or functional gradient descent. And they have both some advantages. So for neural nets, we have automated feature engineering. So for example, for images and text, you don't have to design features. You can transfer learning from one data set to another data set, fine-tune the neural networks very easily. And you can do end-to-end training. So for example, if you have two sources of information, such as text and images, you can have two neural networks, and then you combine the outputs of these two neural networks, and then you compute the loss and backpropagate this loss to update the parameters of both networks. For a gradient boosted decision trees, you have other type of advantages. In particular, you have built-in input for processing. So if for neural networks you have to normalize and scale your input features, you have to deal with categorical features, you have to deal with missing values. For decision trees, you often get this functionality for free, and you don't have to bother by doing a lot of pre-processing. It's also efficient for heterogeneous data. So if you have multiple sources of information in your data, for example, you have social network with people, and people have gender, and they have income, and they have alma mater, and city where they live, it will be much more efficient, and it was demonstrated by a lot of experiments by using gradient boosted decision trees. And finally, you get outcome interpretation, so you can understand which features are important and which are not with decision trees much more easily by looking at the number of leaves that have a specific feature. So there's much more explanation happens in gradient boosted decision trees. And the question that we ask, can we get the best of both worlds when we combine graph neural nets and gradient boosted decision trees? So first, a few slides on graph neural nets. Graph neural nets is a black box. It's a function that takes as an input a graph and the node features, and then it outputs new node features. So the graph structure remains the same, but the node features change. And in fact, these node features can be of arbitrary dimension. So if you have a prediction task and we try to predict the classes, then this vector would be of cardinality of number of classes, because for every class you predict the probability. And then it has this two functions, combine and aggregate. So you probably all know how graph neural networks operate. They take a node, and they take its embedding, and then they aggregate the neighbors that it has by applying some aggregate function, which could be any function like MLP, for example. No, aggregate should be actually invariant. Yes, invariant function to the order. So it could be, for example, be a sum or the mean or something else like RNN. And then you have combine, which is any function such as MLP or any other nonlinear function. And as I said, you get at the end new node features. And then how do you train it? Well, you train it through stochastic gradient descent. So this is what you get as an input. You get the graph and you get the node labels. So you get the node labels only for a part of nodes. And then GNN gives you new node features. Then you get the tables of node features. And then you put these node features to MLP. MLP gives you predictions. And then you compute, for example, coarse entropy loss. And you do stochastic gradient update for the parameters of MLP and for GNN. So this is all, we all know this, we all love this. That's very easy to understand. Now, gradient boosted decision trees are very different models in terms of how they are used and also how they are trained. So GBDT, they map features to predictions. So first of all, there is no graph involved when you deal with gradient boost decision trees, and there is no way to apply GPT on graph data by default. So instead, you can have a vector of features, and then this vector of features has 4 features in this example. And we go one by one, starting from the root. And root asks whether x2 is less than 10. If yes, part of the data goes to the left. The remaining part of the data goes to the right. And so on. So you proceed, and at the end, you get some prediction of what is the label for this particular vector. And you also do the same for the second tree and for the third tree and so on. And then you sum the predictions for every tree, maybe with some weights. And the way how you create a new tree, you create a new tree such that the loss of combined trees of the previously built trees and the new tree will be minimal. So you try to find a new tree, H, such that when you combine it with previously built trees, the loss function for all the trees will be minimized. And this is the whole idea of gradient boosted decision trees, that you don't update the parameters as in neural networks. Instead, you add additional trees to improve the loss. So this is high-level idea. So let's now understand how exactly do you train the gradient boosted decision trees. And to understand that, you first have to understand how decision trees are trained. So this is maybe basics for you. Maybe you already know it, but I'll give you an overview so that you understand the whole idea of GPT and our model in particular. So when you try to do a decision tree training, you get the data, which is in tabular format. So you get a table of features and you get a label for each vector. And then you try to build a tree from the top to bottom. So you start from the root, and then you look at all the possible splits that you can have in your data. So the splits mean that how different features vary from each other. So you can see that x1 has 2 possible values. It has value 4 and has value 5. So the 2 possible splits that you can have is x1 less than or equal than 4, and also x1 less than or equal than 5. The same for x2, you have 7, 8, and 9, so you have 3 additional splits. And for x3, you have 2 additional splits, so it's x3 can be equal to 3 or to 2. And now we have to choose a particular split for this root. So there's some math how you decide. It's not very complicated. The whole idea is that you try to select the split such that when you put it at this node on the tree, it will separate your data in such a way that some criteria is minimized. So in this particular case, when we do regression, the criteria is mean squared error. And so what is written here, it's written the loss function. So the loss function tells you that if you look at all the data that was put to the left, what is the value of the criteria, and what is the value of the criteria for data that went to the right subtree. So for example, let's say we select this condition x1 and 4. So that means that the root will be f1 less than 4. Now we split the data according to this condition, and so you can see that on the left we have all the rows from this original data set that for the first feature have 4. And for to the right we have another part of the data which don't satisfy this condition, so it has 2 rows. And then you go directly for this formula, so you compute y hat, which is the average label that you get in this data. In this case, you have 2/3. And for the T right, you have all labels equals to 0, so the average label equals to 0 as well. And then you compute this criteria, which is mean squared error. And for the left subtree, it would be 2 over 9. For the right subtree, it would be 0. And when you combine, you get the final loss, which is 2 over 15. And so what you got is you got this criteria that for H1 and 4, the loss function will be 2 over 15. And then you do the same for all other conditions. So for example, for x1 and 5, for x2 and 7, you get some different losses. And then you pick the one that gives you the minimum value. So among all of the splits that you have, you pick the right, the minimum, the split with the minimum loss value. So in this case, it's the first one. So that means that you will put this condition to the root of the tree, and then you will move on with your data, and you'll try to do the same for 2 new children of this root. So you build 2 new conditions and so on, and this is how you build the tree. So by deciding how many levels do you want to have in the tree, you build as many conditions as you need, and at the end you have leaves, which are just the average labels of the data that appear in the leaves. So this is how you build a single decision tree. Now, when you understand this, you understand how to build random forests, or more generally, gradient boosted decision trees. So how do we combine trees in gradient boosted decision trees? The idea is the following. So you get some input data, which is x, x1, and y1, and so on. You build the decision trees as usual. So this is your training data. And you build the first decision tree as I just described to you. And this decision tree gives you a vector of prediction. So for every row can go through this tree, and it will end up in some leaf. And this leaf gives you a prediction. So then you stack these predictions. T1x means it's the vector of predictions. And then you can compute the loss between this T1x and the true label. So for the first row, it will be y1. For the second, it will be y2, and so on. So you will compute the loss function, and this loss function could be different for different problems. So for regression, it's usually MSE loss. For classification, it's usually cross-entropy loss. And this MSE loss, it's a simple mathematical formula. So just a difference between two values squared, and then you can take the gradient of this loss function, and on the second tree, the whole idea of gradient boosted decision trees is that the second tree tries to approximate not the original label, but it tries to approximate this minus gradient of the loss function with respect to prediction that it made, so to this value. So why do we do this? Why do we predict with the second decision tree the minus gradient? It is because when you will add trees together, when you add the predictions of the trees, the second and extra trees, the future trees, they will try to reduce the error by following the gradient step in this loss space. So it will try to minimize the loss by adding new trees. So if your second tree is really good in optimizing these values, if it gives, for example, 0 MSE error, then when you combine the first tree and the second tree, it means that your error, your loss that you got in the first tree, it was improved by following the gradient direction. of the second tree. In all cases, what you do with the second tree, you try to approximate this minus gradient, as I said, and it will build you a new tree with new values on the nodes. And then you can sum the first and the second tree. You can sum the predictions. It will be a new vector of labels. And again, you can compute the loss function here between these predictions and the original target labels. And it will and compute the minus gradient again. So what you do is you build the first tree with the original labels, you compute it minus gradient with respect to the prediction that the first tree made, and then the second tree is trying to approximate now not the original labels, but it tries to approximate these gradient steps that you need to make in order to decrease your loss function. And one question that you may have is why do we need to approximate minus gradient? Why not to approximate something else? So, for example, you could approximate plus gradient, or you could approximate, for example, the finite difference between the T1 and Y. And the reason why I approximate minus gradient is that's why the whole procedure is called gradient boosted decision trees, is that the minus gradient gives you the direction of the largest improvement to your loss function. So that's why gradient descent works. We know that by following the gradient, we'll decrease the function by the largest value if you select the step size properly. But you could, for example, also approximate not the minus gradient, but you could also approximate the finite difference between T1 and Y label. And in that case, it would be called boosted decision tree, so there will be no gradient boosted. Yeah, and so the second tree approximates this minus gradient, and then you repeat this procedure. So the third tree will approximate this minus gradient next, and so on. So you can build every new tree by improving the error that you got, the loss value that you got in the previous iterations. And here's the node. Maybe it will give you additional insight. So when you think about gradient descent, we all know how gradient descent works for neural networks. So you have a function that is a parametric function, so it has parameters. For example, it could be MLP, it could be any other neural network. And this function, it maps, as I said, graph and the node features to the same graph and the new node features. And when you do the gradient descent, what you do is that you update the parameters. So your new parameters are the old parameters minus the gradient of the loss function with respect to these parameters multiplied by some step eta. And if you choose the eta parameter correctly, it shouldn't be too big, then you're guaranteed that your new loss function will be better than the old loss function. And the whole process converges to some local optima. Now, if you look at the gradient boosted decision trees, you can see that there are no parameters at all. There are no parameters that you optimize constantly. There's nothing like in neural networks. Instead, in gradient boosted decision trees, what you have is you have a sum of different functions. So each function, in the case of dt, it's a tree, but it could be actually any other function. So you could, for example, do gradient boosting not on the decision trees, but on neural networks, and in which case it would be called gradient boosted neural networks. But for some fundamental reasons, people use decision trees. In fact, you have to have some very simple what is called learners. So these decision trees are called learners, and there is a concept of weak learnability, which means that you have to you have to be you don't have to create a very complicated function for GPT. In fact, you strive to have a very simple decision tree for this. And GPT is just the sum of these functions. And each function is frozen, so you never update the parameters of this. Once you build the decision trees, you keep it for the remaining of the rest of the procedure. So, and the way it's built is that you start with some predictor. So, for example, it could be a constant predictor that would just give you a constant value regardless of which features it takes in. And then every new decision trees, the way it's built is that you take all of the previously built decision trees, predictors, and you do again, you add additional decision tree, which would correspond to this minus gradient of the loss function with respect to the predictors that you had, multiplied by some step size eta. And in this case, again, you get this guarantee that the whole procedure converges to some local optima. And you, by adding additional tree, you improve the loss value. And now you can see that if in GNN we were doing gradient descent in a space of parameters, you had a space of parameters, and then you navigated yourself in this space of parameters. So you can imagine like a 3D world of parameters, and then you start at some point, and every new update to the parameters, it just moves yourself in the space of parameters. But in the GPT, what you do, you have a space not of parameters, but you have a space of functions. So you start with some function, and then you move in the space of function by adding additionally some tree. So I hope that this gives you a little bit of intuition and explanation of how the GPT works. If you have any questions, please let me know. If not, I will move on to the Boost GNN. So that was just explanation of the background. So that was explanation of how GPT and GNN work. And now the whole Boost GNN, how does it work? So in the Boost GNN, what we want to do is we want to apply gradient boost and decision trees to the graphs. And as I said, it's not possible by default. Instead, what we propose, we want to extract first the node features of the graph, then put it through GPT. GPT will give you predictions for every node, and then you will use these predictions from GPT on top of the node features that you already have. So you update the original node features by adding this f of x, which is the prediction of GPT. And then you do the GNN part. So GNN will compute the loss function given this graph and the new node features. It will compute the loss, and then you can take the gradient of this loss function with respect to the node features. And remember that because we had the node features augmented with the predictions of GPT, you can now take the gradient of this loss function with respect to the predictions of GPT. And this way, you can build the second tree by approximating this minus gradient of the loss function with respect to the predictions from the first step. So there are a few advantages of this approach. In particular, you inherit the data preprocessing part from GPT. So, for example, existing software, they deal with categorical values, they deal with missing values. So you don't, if you have a graph with nodes that have categorical features, now you don't have to worry about preprocessing steps because GPT will take care of this. Now you can plug this model, GPT and GNN, whatever you want. So for GPT, you can, for example, pick XGBoost, or you can pick CatBoost, LightGBM. And for GNN, again, you don't it's GNN agnostic, so any GNN model that you have, you can plug this inside this whole pipeline. This is trained end-to-end in the sense that you don't train GPT and GNN separately, but you actually build GNN and GPT together. So GPT takes some input signal from the graph. And finally, there are two interpretations. You can look at the whole architecture as a GNN with embedding layer coming from GPT. We can look at it as a normal GPT, which has a parametric loss function, which is parameterized by the GNN. And now, how do you actually train this procedure? So when you build the first tree, what you do is you get the graph. You first compose the node features for this graph. You build the first decision tree with this input data. And then you get the predictions from this decision tree for every node. For every node, you can get a prediction. You append these predictions to the node features. Now you get this new graph G, you get the same graph G, but you get new node features X prime, augmented with the predictions. You then put this through GNN, and GNN computes you predictions for training nodes, and it computes you the loss function. And then you do is typical stochastic gradient descent. You update the parameters with this loss function. You update the parameters of GNN, and you also compute the minus gradients that the second decision tree will try to approximate. So the second decision tree instead is approximating now the minus gradients, and it repeats the procedure. So it builds the second decision tree. It gives you new predictions for the nodes. You update these predictions for every node feature. You put it through GNN, you compute the loss, and you repeat it. And you do it for as many decision trees as you want, and for as many parameter based to GNN as you want. And in terms of the inference, so when you already built this whole Boost GNN pipeline, how do you do inference? Well, you do it in a similar way. You get a graph. You first get the set of node features. You path it through the GPT. You get the predictions. Then you update the node features with these predictions. And then you pass this graph and the new node features through GNN, through the trained GNN, to get a prediction for every node. So this is how you apply this Boost GNN model. And now going to experiments. So we verified this model in semi-supervised node classification and regression tasks. In particular, we use data sets with heterogeneous and homogeneous node features. So by heterogeneous, I mean that these node features have a lot of different data types and scale and sources of information, while homogeneous usually mean that the intuition or information that you get from the node features, it's uniform for all the nodes. So for example, for Wiki dataset, we have homogeneous node features, and in this dataset, the features are back of words for the articles in the Wikipedia. So because back of words features are very homogeneous, so it's either 0 or it's some number, it's well suited usually for neural networks. While, for example, for house dataset, it's the geographical map of houses, and each house has features such as number of people that live in this area, the area of the house, the traffic is around the house, and so on. So this is very different types of information that you get. Next, we compared against the baselines such as GNN, GBDT, and also MLP. And for all the models that we had, we did hyperparameter tuning, and we ran the models to the best of their abilities. And so the results for node regression and node classification are quite interesting. So they indeed show quite a good improvement for this data set with a lot of hyperparameter tuning. So for example, for house data set, we get, so this is our model, BGNN. BGNN gets 8% of improvement in terms of the RMSE loss function, 8% of improvement if you compare it against graph attention network. So you can see the second column gap in percentage, the smaller the better. And you can see that BGNN works really well if you compare it to GNN, or if you compare it to GBDT alone. So for many data sets, for heterogeneous data sets, indeed we get much better performance with BGNN. The same thing happens for node classification. For node classification, we also look at the accuracy. So now the higher the gap, the better. So for example, for data sets like house classification data set, we get 9% better accuracy than graph attention network. We also looked at how different GNNs impact the performance of our model. So we looked at 4 different GNN models, such as graph attention network, GCN, AGNN, APPNP. And we looked at what is the improvement we get. So again, here, the smaller the bar, the better. And you can see that this red plot, which corresponds to BGNN, it's always better than the original implementation of the graph neural network. And in terms of training time, one may think that because BGNN, BoostGNN, is composed of 2 models, it's composed of GBDT and it's composed of graph neural network, we will incur larger training times. And in reality, it's not the case, because in reality, what we observed is that BoostGNN converges really fast. So already after 10 epochs, after 10 iterations, it already gives you the final optimal value. While, for example, for GNN model, you can see it's here in the blue, it usually takes hundreds or thousands of epochs to converge. And that's why when we look at the time, so here's the time in seconds, you can see that, for example, with BoostGNN, it takes 20 seconds to converge for the house data set, while for graph attention network, it takes 35 seconds. So it's actually a noticeable improvement for many data sets, not only in terms of the quality of the results, but also in terms of the speed of convergence. And this is pretty much it. There is more results in the paper, but the main message here is that for data sets for graphs with heterogeneous node features, such as house data set, for example, when you have multiple data types and scales of your data, it's advisable to use this model, BoostGNN. For standard data sets such as Quora, CiteSeer, PubMed, Open Graph benchmark data sets, they all have very standard node features. And in these cases, it's okay to use graph neural networks, and they could be state-of-the-art performance. But as you go to some real data sets, they usually have a lot of heterogeneous information, and therefore it's useful to use this model. So thank you very much, and if you have any questions, please let me know.
Yeah. Hey, Gabriele, do you want to talk?
Yeah, so I can do that. So thank you for the presentation. It was really nice, and I enjoyed it a lot. So an interesting topic. And is there any question from the audience? Or otherwise, I have a bunch, so I can start. Then, if someone wants to jump in. So the first thing is if I just a technical thing about the training of the method. So if I understood it correctly, when you add the, let's say, when you are in the second loop of the update of the of the tree, do you need to retrain the graph neural network from scratch, or can you reuse some, like for example, use the old parameters as initial values or stuff like that?
Yeah, so you don't retrain it. It's a good question. You don't retrain it. You continue to train it. So
you update, let's say.
Yes, you continue to update the parameters.
Okay. And did you observe some kind of local? No, I mean, it looks like it works very nicely. So I guess that you didn't observe something like that, but you can. It's not the risk that you are too close, because I can imagine that as the training advance, your additional features they converge to some value probably, right? So they go closer and closer to some value. Okay. So probably your loss. So you stay closer to the same minimum, because you don't change the features too much, right? So do you observe something like that, like
yes, okay. Yeah, it's a good point. So in some cases, indeed, the gradient here that you get, it becomes zero, because you actually don't you kind of converge to the node features already. So in that case, you just stop the procedure, because if all of the values for decision tree, if all of the labels that you try to predict equal to zero, then you cannot really incur any additional information. You just stop the procedure. In our cases, yeah, what we try to do is we observe that original labels could be, for example, of any scale. So you could have regression tasks of prediction, for example, click-through rate, which could be be very small, or it could be the prices of the house, which could be very large. But the second and the third and so on trees, they predict very small values still, because they get this gradient update, which is usually very small. So it's just the difference between the new and the old features. Yeah. So in general, yes. In the code, sometimes we encounter the situation when it converges to some values. In general, it's still, like for many data sets, you don't have this problem, you don't have this case, and you still can continue training it for many iterations.
I mean, it's nice from a theoretical point of view, because if the new features convert to something, it looks like your gradient boosting is converting to something. So I think it's a nice feature. So yeah.
Yes, yeah, indeed. It's also an interesting question whether the whole pipeline converges in theory, because we have thought about it, but we haven't proved anything about it. Not because we didn't know, but because we didn't have time to analyze this. It's a good question whether the boost GNN model has the same convergence properties as the graph neural network, for example, which is known to converge to some local optima. In our case and experiments, we see that it converges, and it converges actually pretty fast. So maybe there is actually better guarantees in terms of convergence.
Yeah, it's nice that by adding a variable, so you increase the dimension, so you have one additional direction to escape local minima, actually. So I think it would be nice in that respect. Okay. And related to this question, so do you consider, instead of adding, so now you keep updating one only, so you have a bunch of given features, and then you compute a new one, and you get better and better in computing these new features. So did you consider instead adding a sequence of new features? So every time you update, you add let's say that every new update gives you a new feature in your feature vector, let's say. Because otherwise you still have one new feature versus all the old ones, let's say.
I'm not sure I got the question. So what is the proposal?
So let's say in the example that is shown on this slide, you have 3 original features, and then you construct a new one. And this is for the first 3. But then when you construct the second 3, so not the second 3, but the second iteration of the gradient boosting, you have a new feature, right? So, or an updated version of the old blue one.
Yes.
But you can just append it to the list. So in the second iteration, you could have 2 blue, 3 red, let's say, something like that.
So I don't know if it's technically possible, because your GNN should operate on the same dimensions, input dimensions. So if you continue to increase it, you have to somehow, you could, for example, append it, and then you project. So you could have, for example,
a PCA or something.
yeah, like do PCA on the same 4-dimensional vectors. But yeah, like by default, it would be hard to have variable lengths dimension, input dimension.
Okay, yeah, thanks. And I would like to, so are other people that want to ask some question? So
Yeah, actually, I would have some question. I don't know if you can hear me.
Yes.
Thank you, Sergey, for the talk. It was really nice. I wanted to make a question that I think that it's almost on the same matter that Gabriele was talking about. One thing that I don't really understand, I'm not sure that I get it right, is that the feature that comes out of the GDBT, it's concatenated to the already pre-existing one, right?
Yes, so there are two parts. One part is that you can concatenate it, or the second part is that you can completely ignore the original input features, and you just put the new prediction. So it becomes a vector of dimension 1, and then you provide this vector of dimension 1 to GNN. And in fact, we analyzed it in the paper. So both of the variants are possible. It's either what we call concatenation, or it's replacement of the old features with the new feature. So these are two possible options that we have tried and we implemented. They actually work differently for different data sets. We found that sometimes one works better than another, and in other data sets is the opposite. We have some intuition why it can happen. So in particular, I think for data sets that have a very large-scale target values originally, then it's better to use the only single prediction. And when you have small ones, it's better to use concatenation of the two. So it's our intuition, but in general, there are two options right now, and it's possible, of course, to create another option. It's not a problem. We have experimented only with two.
Yeah, okay. I think that the point could be that the scale of the feature that you're adding is different from the existing one, so you have to take care of the fact that they are normalizing.
Yes.
I think that. And another question would be about the training scheme. So at each epoch, you train a new tree. I understand that correctly, or I mean, how many epochs do you update the GNN before adding a new tree? I mean, it is an hyperparameter of the model or something like that.
Yeah, so it's a good question. We actually, before answering this question, I must say that this model is implemented in DGL right now, so it should be part of the examples that exist in DGL, and maybe it will be a model inside of DGL so that you can just import it. And in fact, it's a good question, because the number of trees that you build per epoch and the number of updates that you make for GNN, it's the parameters of the model. So you can, for example, build 10 decision trees and then make 10 gradient steps updates for GNN until you start changing the target labels for the tree. So here I say that we build the second tree. In reality, for every epoch, you could do the following. You can select, for example, build 5 decision trees for this target label, create a new prediction, and then, for example, train GNN for 5 gradient steps or for 10 gradient steps. We have analyzed how does the number of step updates matter. And we found that because if you build a single decision tree at each epoch, then it would probably not very good predictions by this tree. So if you build 10 decision trees, for example, your predictions would be already quite good, and that would be useful. So in the experiments, it's in hyperparameter search that we did. We explored 3 different values: 1, 5, and 10, and I think maybe 20 in some cases, to choose from how many trees and how many updates do we need to make. If you do 1, it converges. It runs faster, but it's actually gives you a little bit worse performance because of this worse predictions by the decision trees. So I think in most of the cases it was 5 or 10 trees and updates for GNN that you have to make in order for this whole model to work both fast and effective.
Thank you very much.
Thank you.
Okay, so is there any other question? Okay, so thank you again, Sergey. And I also want to remind everybody that Sergey is the admin of a Telegram group, which is very nice for geometric deep learning. It keeps you updated on all the latest research paper and outcomes in the geometric deep learning environment. So please check it out. I put the link in the chat. And thank you again for your presentation, Sergey. So see you next week. And in 2 weeks, we're going to have the last tutorial. So bring your ideas there. Okay.
Okay, thank you, guys.
Thank you.
Thank you.
Thank you.
Thank you. Bye.
Bye-bye.